In this part of the tutorial, we will first give an overview of the issues observed during monitoring deployed machine learning models, starting with some of the model performance degradation related issues. One of the common types of issues that is observed is drift of different types. So by drift, we mean changes in certain distributions. For the purpose of this section, let's assume that the model under consideration is a binary classification model. So for example, here is a model which is represented in a two-dimensional space with perhaps say two features. The blue and yellow correspond to the labels of the model, correspond to two different classes. And here is the decision boundary and the training data that is used to train the model. Let's consider the probability of the target variable. In this case, the color of the circle denoted here, given the input X, which is represented as the feature vector here. First type of drift is what's often called a concept drift, or sometimes called real concept drift. Here, the relationship between the target variable and the input features changes. So in other words, the probability of Y given X changes. This can occur due to changes in perhaps real world conditions, even if the input does not necessarily change. Like, for example, in this illustration, we can see that the distribution of inputs has remained the same. The points are where they were, and even the most of the class labels are as before, but the relationship has changed. So another type of drift is called a data drift. So here the data distribution, the input data distribution, or the features themselves change, even if the relationships between the target variable and the input features may not have changed. So often this may not be as much of a concern. Like, what we really care about is being able to identify concept drift as opposed to just data drift. There are also other terminologies used in this community. So one is label drift, wherein the probability of the label distribution changes. The other is feature drift, wherein the probability of the input data, or P of X, changes. Either of these doesn't necessarily mean that concept drift occurs. It is possible for just the label distribution to change or the feature distribution to change while the relationship remaining intact. Let's consider a setting where the label drift happens. This, as I just mentioned, this doesn't necessarily mean that the concept drift has occurred, and as a result, this does not necessarily affect the model's accuracy, but it can still affect the underlying business. For example, if the ratio of people eligible for loans suddenly increases or decreases, that may lead to a loss of opportunity or decline for business in the case of a lending company. So likewise, the feature drift may not necessarily correspond to degradation in the model quality, and often some level of drift in the data distribution is expected over time. Just like label drift, this can also still lead to certain types of issues. For example, if the model starts seeing data it has not seen during training time, it may not necessarily behave as expected, even if the underlying relationships have not changed. Finally, the terminology virtual drift refers to the setting where the different types of drifts may have happened. For example, the relationship may have changed, but the decision boundary used by the model may still work as before. So as a result, that may not have as much of an impact as far as the model itself is concerned. Let's make this concrete using a loan application model. Here, let's look at when concept drift can occur. Consider a setting where the income level that was considered creditworthy earlier may be now considered riskier. So this can happen in the case of macroeconomic factors, which may cause lending to be riskier than before. And as a result, there may be a higher standard for deciding whose loan application should be approved and whose should be rejected. Another setting is label drift. Uh, an example of this might be a larger proportion of creditworthy applications may start showing up. This may simply be because the model may have been trained on the overall population, but may have been deployed perhaps in a more affluent area. As a result, the model starts seeing applicants who are more affluent and consequently maybe more credit worthy than the general population. The third example is feature drift. This is a setting where the incomes of many applicants may increase or decrease, or we may get more applicants from one particular geographic region or one particular demographic. Again, this might also have a tangible impact on the underlying business metrics. Next, let's look at what are the factors that may lead to such types of drift. Broadly, we can categorize this into two types. The first one is what I have denoted here as real change. So this corresponds to a setting where the label distribution or the feature distribution can change. For example, there may be a product launch in a new market, and as a result, the input distribution as well as the output distribution may be different. Or in the case of, let's say, a pandemic or a competitor launching a new service, the relationship between the target variable and the input features can change, or the concept drift can occur. In these cases, often we may have to retrain a model or perhaps come up with maybe newer features, different set of features, or collect different types of training data and train a different model possibly. The other type of trigger is the broad class of issues which are called data integrity issues. This is a setting where the underlying foundations have not changed, but the data that is fed into the machine learning model may be corrupted. One setting where this can happen is the correct data is obtained at the source, but due to some bugs in the data engineering pipeline, things might get misrepresented. For instance, somewhere in the pipeline, values for age and debt to income may have been swapped, and that might cause an issue. Or it's possible that somebody might have made a change from, say, inches to centimeters for some measurement, but that may not have been reflected downstream. And as a result, the machine learning model might expect the value to be in inches, but instead is receiving the value in centimeters instead. The second type is incorrect data. It may be entering at the source itself. This could be due to, let's say, a bug in the front end. Let's say a website form accepts even if a field is left blank. As a result, that entry may become missing or may get corrupted. So next, let's discuss how we can detect these issues. Again, like we want to broadly group this into two buckets. The first bucket corresponds to the setting where we may have access to labels, and the second bucket corresponds to the setting where we may not have access to labels, or we may have to make decisions solely based on data distributions and the changes in these data distributions. Under the first category, we tend to apply this kind of techniques when we have access to ground truth or labels. If there is a mechanism to obtain ground truth labels almost in real time, we can keep track of different quality measures of the model almost on a real-time basis, and see whether some of these quality metrics may be dropping over time. There are a variety of, again, different types of techniques to achieve this. I would encourage you to take a look at this excellent survey on concept drift adaptation. But let me emphasize that in many real world conditions, we may not get ground truth labels immediately, or even if we get ground truth labels, it may be after a subsequent period of time. For example, if you consider lending settings, we may not know the ground truth until after the borrower has repaid the loan or defaulted on the loan. And this holds true for many other real world settings as well. In those settings, we may still want proxies to gauge whether the model may have degraded in performance. There are different types of such proxies. One proxy which is kind of intriguing is one where we look at the features that are important for the model and see whether the set of important features is changing over time. If the set of important features is changing, or the relative importance between these features for the model prediction is changing over time, it could be an indication that concept drift may be occurring, even though we may not have access to ground truth labels, and even though we may not be able to measure the model accuracy directly. Next, let's look at the second category. First, let's consider the setting where it might still be a supervised learning setting, like say binary classification, but we do not have access to ground truth labels. So in this case, we may want to measure changes in the distribution of underlying variables. For instance, the distribution of features or the distribution of the prediction probability itself. There are several different statistical measures commonly used to compute these differences, such as Jensen-Shannon divergence or KL divergence, population stability index, and so forth. These can be applied either on the prediction probability distribution or on the feature distribution themselves. While these are parameterized in some sense, one could apply non-parametric tests, such as the Kolmogorov-Smirnov test, to determine if there may be a drift in the data. Next, let's consider the setting where we may have unsupervised learning settings. Once again, I would not be going into the details, but I refer you to this article, which provides an overview of unsupervised drift detection methods. There are different types of trade-offs of this class of methods. They can often be more accurate, but they tend to provide an overview of the global picture, and as a result, they may miss gradual drift or sensitivity issues associated with the model. In addition, often this class of methods may not be easy to explain to a non-technical user, such as a business or decision maker. Next, let's discuss what do we do once we identify different types of drift issues. Again, like here we are divided into two buckets. The first is figuring out whether data integrity issues may be causing the problem. The second is, if not, to identify what may be the underlying root cause for the changes. In terms of data integrity, again, like there are either data integrity, or you could also think of them as monitoring for outliers. So unlike in non-machine learning applications, the machine learning applications tend to be very forgiving. And even if incorrect data or missing data is fed to the machine learning model, the model may still produce an output, just that it may not be as reliable as before. Yeah, so there are different types of data errors. These can range from missing values, or say range or type mismatch, or even schema mismatch, changes in the unit of measurement, swapping of maybe two features, and so forth. Again, this can be due to data pipeline bugs, or possibly changes in some parts of the system which may not be reflected in other parts of the system, or even possibly changes in the business itself. The second category here is what we call drift analytics. So this is one where we want to understand the root cause of the drift by performing attribution to different possible causes. For example, here we are seeing a screenshot from the root cause analysis of drift using Fiddler's model monitoring platform. So here in the topmost chart, we see the drift in the prediction probability. And once we have identified such a drift, we then want to attribute that drift to different features, in taking into account the importance of the features themselves. And then we may want to go deeper and look at the changes in the features themselves, in terms of the changes in the feature distribution between two different points of time, and try to find out whether there may be outliers or other issues that may be causing this. And then once we identify such changes in the feature distribution, we may want to then slice and dice the data by trying to determine whether the change is predominantly coming from, let's say, one geographic region or one subgroup of the data, as opposed to changes occurring across the entire spectrum. Having identified the root causes, let's look at what may be different types of ways to fix the issues. So one type of fix is to update the pipeline. This works in the case of data integrity issues, wherein we can make sure that the schema changes are correctly reflected, or the violations are fixed, and so forth. The second type of fix might be one where we may decide to retrain the model, or perhaps adapt the model to a subclass or a different setting. This may involve perhaps reweighing the data points, or applying appropriate business logic, and so forth. The third category is one where we may want to think of this as managing the model as a whole. This might involve perhaps archiving models on a regular basis, or retraining on a regular basis, and comparing one model versus other models which may be related, and so on. So with this context, let's now look at model issues for deployed models beyond model performance. So what do we mean by beyond model performance? This can range from, say, notions like bias and fairness, or transparency, explainability, privacy, or robustness, and so forth. And the reason to consider these different dimensions is that even if the model continues to maintain accuracy, it's still possible that the model may start exhibiting differential performance for different groups over time. And as a result, certain subgroups of the population may not be experiencing the same level of quality as during the model training or model validation time. So specifically, let's start by focusing on fairness and bias. First of all, how do we go about approaching fairness or bias in a practical setting? So here there are two broad notions. One is from the perspective of the policy aspects, and the second is from the perspective of technology aspects. When we say policy or process aspects, so it starts with identifying what are the goals for this product, what are the acceptable trade-offs between, say, accuracy and any potential bias present in the model. We may want to get all the relevant stakeholders as part of this decision-making process. And this should include those who may also be impacted by the model. It's important to make sure that when we collect the set of stakeholders, there is representation from people with different demographic backgrounds, different lived experiences, different disciplines, and so forth, so that we do not have any blind spots when deciding what are the right choices for the model to start with. Of course, this involves identifying the relevant stakeholders. So once we have addressed these issues, then from a technology angle, we may want to decide what may be the most appropriate fairness notions and corresponding metrics for the specific machine learning model setting. So once again, the fairness notion has to be decided by taking inputs from all relevant stakeholders and the application context in mind. Next, we may want to analyze and evaluate the system, both the machine learning model and any associated business logic surrounding the model. Then if we observe any issues, we may then want to figure out how to mitigate the issues. And the key aspect I want to emphasize here is that we not only need to do this during model validation time, but also need to monitor this continuously and have plans for escalation if certain types of biases are observed once the model is in production. What should the remediation be? And it's good to think through these escalation plans beforehand. And notions like auditing and transparency also go hand in hand with all of these issues. So more broadly, we can think of fairness being incorporated into all aspects of the machine learning lifecycle. This starts with the problem formation, asking ourselves whether using a machine learning approach is even desirable and ethical for the specific problem setting. Next, when it comes to data set construction, we may want to ensure that we have data representative of different groups, and if there are any biases in either labels or features, we may want to figure out how to mitigate those biases. Then during model training, we may want to incorporate fairness constraints. And similarly, during testing, we may want to test the model for performance for different groups. During the time of deployment, starting with A/B testing, it's often desirable to understand whether the model has unequal effects across different users. Even if during A/B testing, we notice that the new model performs better than the old model overall, we still want to understand whether the model has improved performance across all subgroups. Also, we want to know whether the model is deployed on a population for which it was never intended. The model may have been trained and evaluated on an altogether different population or different purpose, and we may be deploying in a completely different setting. While in certain cases it may be fine to do this, it's important to be cognizant of that change and ensure that the model still works well for this new population. Finally, we may want to understand whether the model has any feedback effects which can result in increasingly unfair outcomes. A classic example of this is the Tay chatbot that Microsoft launched around 2014-2015 timeframe. And because of feedback effects, this chatbot started exhibiting biases very quickly. And more broadly, we want to keep monitoring the deployed model for different types of bias metrics. So let's look at how this can be operationalized from an engineering angle. So here we are again showing the same kind of machine learning lifecycle, but in a linear form here. All the boxes in yellow correspond to the steps where we may want to incorporate fairness interventions. First, at the time of preparing training data, we want to measure any bias in the training data and decide whether we want to mitigate bias by applying different pre-processing techniques. Similarly, during the time of model training as well as model tuning or hyperparameter optimization, then when we decide to A/B test or deploy the model, again, we may want to check whether we want to apply post-processing bias mitigation techniques. And most importantly, once the model is deployed, we still want to measure and monitor the bias metrics over time. So all these steps are perhaps important, and often there tends to be a lot of emphasis on everything to the left of this dashed line, which corresponds to the offline aspects and not as much on the online aspect. Let's look at how this is operationalized from a machine learning deployment setting. So for this, here is a screenshot from Amazon SageMaker. Specifically, this is a screenshot which shows how one can monitor bias for a deployed model over time. Here, the model developer or the stakeholder has chosen two different bias metrics, difference in conditional outcomes and conditional demographic disparity in labels. And they have also set a threshold shown by the orange line here. And whenever the observed bias measure exceeds the threshold in a statistically significant manner, the model developer can choose to get alerted so that they can then decide whether any intervention is needed and any corrective action needs to be applied. So this is done as part of Amazon SageMaker Clarify and SageMaker Model Monitor. If you're interested in details, please refer our papers which appeared in KDD 2021 and 2022 for details. Next, I also want to show how we can similarly monitor drift in the behavior of the model itself over time. So here again, in the screenshot here, we are showing how one can keep track of the importance of different features over time. Specifically, here we are looking at importance of one of the features called A14 associated with a model trained on the German credit data set. And we are looking at how the importance of that feature changes over time across different predictions performed by the model. So here the importance score is obtained using a variant of the Shapley values, or using a variant of the SHAP technique. At the bottom, we see the chart of the different features ordered by importance, and it may not be visible here. We also show whether certain features have gone up in ranking or gone down in ranking. That can also be an indication whether certain features may be becoming less important or more important over time, and depending on the application context, one could again take certain corrective actions. So once again, for details, please refer our paper. So this concludes the discussion about bias and fairness in deployed machine learning models. Next, we will discuss some of the challenges with keeping track of explainability over time for deployed models, and also how to ensure that the deployed models are not prone to adversarial attacks.